Hello, okay. Hello, and welcome to the demo of my implementation of AlphaGo. Here you can see some some code, and if we go into going to run it, when it starts up, basically what it'll do is it will train 1,000 times on the data set that I've already generated for it. So this data set's basically 1,000 random games. It's just to get the AI a good foothold on how to just a good foothold on how to play at the start. So this thing's going to go through 1,000 games real quick. And then once that happens, you'll be able to see some nice statistics here, and the board will show up here. So just give it 1 second. And here we go. So the AI is playing against itself. Right now it's playing a randomly initialized game. So this is basically with minimal training. It's just kind of it's starting the very beginnings of training. And if we look, oh, whoops. If we look over here, on this side, if we pause this real quick, you can see it displays the number of times it tries every single possible move in each case, so 12, 13. It has a pretty uniform preference over moves at this point because it's still early in its training. And then here is the amount that it believes that it's going to gain, basically the the probability of winning, or the change in the probability of winning if it selected each of these moves. So, for example, if we look down here, the worst move in this case. Well, you don't know who's playing right now. Anyway, so we can let this run in the background, and then if we go here, this is an old training run from back when I let it run for a really long time. So this is it going over 2 million training steps over the course of almost 4 days. And so you can see some cool stuff, like for example, the winner slowly over the course of time becomes black, because in 5x5 Go, black should be able to win every single time. And the ELO nicely goes up and to the right. Not quite. This thing on the bottom here, where it goes negative, is a little bit misleading. This ELO is calculated from from like a significantly hampered version of itself, using much less computational power, playing against older versions of, again, hampered versions. So it doesn't perfectly capture it. This specific thing happens to come from the fact that um, when it's first learning to play, it places a very high value on passing, which usually leads to winning a game. But if you're not playing with extra like rollouts to keep it from passing in the wrong times, then oftentimes, as it learns to pass more often, that will actually make it worse if you don't add the additional Monte Carlo rollouts. But even the pure network just playing against itself learns a significant amount, learns to beat earlier versions of itself and climb to an elo of over 12,000, higher than when it started. So anyway, this was a labor of love, probably one of my favorite projects I've ever done, and yeah, I hope you like it.